It's really great to be with you, even if it's only virtual. I really enjoyed my visit last August when I was at the Tata Institute, and I used the opportunity to come to ISI. So I thought a nice topic for your colloquium that should be of interest to both sort of pure mathematicians and applied mathematicians and people working in statistics and probability is to give you a little survey on big open questions on very, very simple sequences that come from number theory, but also have motivations in mathematical physics, and to sort of analyze their fine scale distribution. So which sequences I'm talking about, I'll reveal in a minute, but let me first start with a sort of general setting. So let's consider a triangular array of numbers. So all that means is that we look at these rows of numbers and we just fix them. So the important thing throughout the talk is that I'll really be mostly thinking about deterministic sequences and how to test sort of the pseudo-random properties. And as I said, these will be very, very simple. And if you like, the whole randomness is created by taking fractional parts of those. You know, you think of this as a sequence of sequences of real numbers. So we take the fractional part, which is just the number minus its integer part. So this will be between 0 and 1. And the first statistical test that you can make is to ask, is the sequence uniformly distributed? Which means if you count the number of fractional parts of your sequence that fall into a certain subinterval AB of the unit interval, then we say it's uniformly distributed if the proportion of numbers that fall into the interval AB is asymptotically equal to the length of that interval, so B minus A. Okay, and equivalently, you can also think of these, of course, as sequences of measures. So you can take test functions, which are one periodic function. So for any continuous one periodic function, if the average over your sequence converges to the Lebesgue average, then we say equivalently it's uniformly distributed. So by the way, just interrupt me if you have any questions. Yogeshwaran, can you monitor the chat? Because I'm not looking at it. So if anyone feels like they want to post a question in the chat, that's fine too. But it's also okay if you just speak up and interrupt me. And by the way,
in case there is any question, I will stop you and ask on the chat.
Perfect. Yeah, yeah. And do feel free to switch on the camera. It's always nice to see some smiley faces or sad faces if you don't like my talk. So that's great. Thank you. All right. So this is uniform distribution mod 1. It's a very old concept, over 100 years old, and number theorists have been trying to understand which sequences are uniformly distributed, what can one say about the error term in the uniform distribution, and so on. So here are a few examples of sequences. So you can, for instance,
Jens, there is already a question, one
Excellent.
periodic. Shiva, you want to ask?
One periodic just means it's a periodic function like sine and cosine. And one periodic just means that the period is 1.
F of x plus 1 is f of x, is
it? Now I'm not drawing it very well, but yeah, no, I do draw it well. So this would be an example of a one periodic function if we repeat with period 1. And so, for instance, you could take an interval, BA, and look at the characteristic function, and then you just repeat it periodically. So that sort of gets rid of the requirement of taking fractional parts here. Yeah. So that's sort of, rather than taking a fractional part and looking at a function on the unit interval, you just periodize it. And that's kind of a really good viewpoint here. And in fact, the Fourier analysis that you can do if you think of one periodic function is a key tool in understanding whether a sequence is uniformly distributed or not. So here, let me start with the first example because it's so nice and trivial. It's basically you just look at a triangular array. So for each capital N, you just look at some sort of picket fence here. So these are the points 0, 1 over n, 2 over n, and so on. And that clearly is uniformly distributed mod 1 just by Riemann summation, if you like. But it's not a very random sequence. So uniform distribution mod 1 is clearly not a good test for how random a sequence really is or how pseudo-random it is. Now, here is another example that I like a lot. And that's what is in the title, fractional parts of powers of integers. So we just look at the sequence of integers and raise it to the power beta, okay? And beta is any real number between 0 and 1. That will be uniformly distributed. Another classic example is, irrational polynomials evaluated at integers. In particular, this example here where we take n to the d is any integer, fixed, and then we multiply it by a fixed irrational number. So in that case, Hermann-Weyl proved in 1916 that also these sequences will be uniformly distributed mod 1. It's a beautiful paper, by the way. It's if you like, the birth of harmonic analysis, because Weyl really develops there the Fourier theory and the famous Weyl criterion that allows you to reduce the problem just by studying exponential sums. So that's a really important paper. You could take the primes and multiply it by alpha. They will also be uniformly distributed mod 1. Lacunary sequences. So these are sequences of integers down here.
Jens, there is a question. Yeah? What happens?
Of course.
Is greater than 1.
So
yes. So when beta is greater than 1, the sequence will also be uniformly distributed mod 1 as long as beta is not an integer. Okay, of course, if beta is an integer, it won't be uniformly distributed mod 1. But if beta is an integer, then we have this case here. Yeah, then we need an irrational alpha. So there is a sort of a counterplay. So you could, the most general case is n to the beta times alpha, and then you need to choose beta and alpha carefully so that you basically don't sit at rational points. So that's what could spoil the picture here.
Thank you.
Okay. Primes, lacunary sequences. I'm just giving you an outline here, just out of interest. Very interesting is if you take the fractional parts of log n, it's not uniformly distributed. We're going to come back to that example at the end of the talk. If you take just a triangular array of IID random variables that are uniformly distributed in 0, 1, then almost surely that array will also be uniformly distributed mod 1. And, something that over the last 20, 30 years has become very popular is the study of random matrices. So for example, if you take the eigenvalues of a unitary n by n matrix, these are n numbers on the unit circle by unitarity, and you look at the arguments of those, that's the wrong pen here, and you look at the arguments of the eigenvalues of these random matrices, then almost surely they'll also be uniformly distributed in the unit. Yeah, another question?
Yes, how do you prove the equivalent criteria in the first slide?
That's great. So fantastic. Yeah, that's really good. So this is actually in Hermann-Weyl's paper. And the way you prove this is by a classic approximation argument where, so suppose you have your favorite periodic function. Let me say this one here. So one thing you can do is you can now approximate this by linear combinations of characteristic functions of intervals from above and below. okay? And then by linearity, you can use this statement to approximate arbitrarily well your continuous function. And because the right-hand side is the Lebesgue measure, approximating arbitrarily well, you need to achieve this with respect to the Lebesgue measure. And that's a classic theorem that you can do this. And vice versa, you can approximate characteristic functions by finite truncations in the Fourier series in L1. And so again, that gives you the other directions, that if you have this for all continuous one periodic functions, you can go back here. So it's really an equivalence. But do look at Hermann-Weil's paper. He explains it all in there. It's really a beautiful, it's one of these papers, you know, there are a lot of papers in 1916, which we can't read anymore today, really, because it's sort of old notation and so on. But if you read Hermann-Weil's paper, it's really a modern mathematical paper. I really like it a lot. And you know, I also recommend this book here, which explains all these things. And proves that all these, you know, all these statements that you see here, maybe apart from the random matrix and the IID case. I'm not sure. Great. Okay, so as I've illustrated, there are many sequences here, for instance, this one, that are absolutely not random, right? And so we need to look at higher order tests to explore whether a sequence or this triangular array is really random. And as I said, you know, we're really interested in deterministic sequences here. So one of the favorite tests that people like to look at is the so-called gap distribution. So we now have a sequence here on the unit interval, finitely many points on the unit interval, and their number goes to infinity. So what you can do here is you can just say, well, what is the distribution of gaps between those points? Now, if you have n points, you will have n minus 1 gaps. And what I like doing, because I like to think modulo 1, I'd really like to identify the endpoints of the interval and sort of glue them together. So I'm also considering the gap that is the one that you get here. So it will be the sum of the distance to 0 of the first element and the distance of the last element to 1. Yeah, so I'm just gluing the two endpoints together, and I'm also going to look at the other gap. So it's a technical point. You can forget about this. And then, yes, we have now n gaps. Their average value is 1 over n, right? Or the average value is 1 over n. So we need to, if we look at the gap distribution, what we need to do is we need to blow them up by a factor of n, and then just simply average over all the gaps that we have. And the question is, will this have a limit distribution for all bounded continuous test functions f? That's the first question. There is another statistics, which is a little bit simpler to look at, which I'm sure you all have seen as well. That's the so-called two-point correlation function, or the pair correlation function. And there are a few other names. So this is the second order statistics, where you simply now look at all the differences between your elements. This extra sum over the integers gives you the mod 1. That's like taking the fractional part. Yeah, so we take a compactly supported function of R here. We sum over all pairs that are not equal. So I'm removing those equal ones because that would just give a 0 here. And then again, because the average gap size is 1 over m, I'm blowing it up by n. We normalize only by 1 over n here, and this is because we count in such small intervals. So if you say fix psi n, and you just look at the sum over m, what you're basically asking, how many other elements from your sequence are within a 1 over n neighborhood to psi n? And because it's a 1 over n neighborhood, we expect only finitely many points to lie in there, okay? And then if you then start summing over n, then it's again an average. So that's why we only have 1 over n here, because the expectation value of how many points you have in a 1 over neighborhood is 1. So that's why we don't normalize by 1 over n squared, but just by 1 over n. Okay, let me give some examples. So here again, the IID case. So you take xi1 up to xi2 IID in R modulo z. So I'm sorry if this is not clear. I think of R modulo z just as, you can just think of it as the unit interval with 0 and 1 identified. You just glue this together, yeah? This is simply a circle represented as a unit interval. So we take those IID uniformly distributed, and then it's a classic result. I think you can find this in, oh dear, in, we need to share again. You find this, for instance, in Heller's book. Sorry, I must have touched the wrong button here. Okay. All right. And so what you see here clearly for independent random variables, the gap distribution is an exponential distribution, right? And the distribution of pairs between points is just uniform. So that hopefully wouldn't surprise you. And in fact, we say that the limiting gap or 2-point function is that of a Poisson point process, because that actually is exactly the gap waiting time distribution for a Poisson point process, exactly the exponential distribution that you see here. And indeed, the 2-point correlation function is exactly the intensity measure if you fix an element in your Poisson point process and you then ask, well, what is the intensity of the point process that you get when you look at all the different elements and their distance to that one fixed element, and that intensity is just a constant. Okay, is there another question? There's a chat. Ah, okay, good. Right. If you look at a random matrix, you have a different answer, and that's the exciting thing now, that we do see different gap distributions. So here, the gap distribution for a large unitary random matrix where you pick it at random with respect to the Haar measure on UN, that we know almost surely is given by the Gaudin distribution, which hated function. It's a Pain-Levé transcendent, and there is a very nice approximate formula that looks like this. So that is the random matrix answer here for unitary matrices. The 2-point function, the limit is a little bit simpler. It's the so-called sine kernel here. So that's a very explicit function. I'm not going to talk much about random matrices in this talk. All I wanted to say is what number theorists got really excited is when they realized in the 80s and earlier in the 70s, due to some theoretical work by Montgomery, that the gap distribution and the 2-point correlation function of the zeros of the Riemann zeta function, if you order them on the critical line, follow those statistics. You will have heard of the Riemann hypothesis that says all of those zeros should be on the line, and they all seem to be if you do the numerics. And then you can ask about the distribution, the statistical distribution, and they are exactly following those of unitary random matrices. It's still a huge mystery. And there's been a lot of work on it. People have more insights now, but the problem itself is unsolved. I wanted to talk, as I promised, about much simpler things, much simpler things. And the first result where one can really understand everything is when you take the fractional part of lacunary sequences. And if you don't want to know what a lacunary sequence is, just take this one. This is a nice example. So you just take 2 to the n, and then you take 2 to the n alpha mod 1, and look at the fractional parts and look at the distribution of gaps. Rudnick and Sararescu, who are two distinguished number theorists, proved that indeed the gap distribution and the 2-point correlation function is the same in the limit as that of a Poisson point process. And they didn't only prove it for those statistics, but for all higher correlation functions. This only works for almost every alpha. And what you're really using here is the exponential increase of those lacunary sequences, which really introduce a mixing property. So they behave really like weakly dependent sequences of random variables. And that's what is exploited here in this proof. So that we are comfortable with, that we understand. But like the problem of normal numbers, here we have not a single example of alpha for which we know that this theorem is true. By this I mean, we do not know whether it's true, for example, for alpha equal to pi. Yeah, so if you give me any number, I can't tell you whether this theorem holds for this number, unless it's constructed to be a generic number with respect to the Lebesgue measure. I want to study even simpler sequences. So for instance, as in the title advertised, n to the d, yeah, powers of polynomials. And then, as I said earlier, in order to have uniform distribution, we need to assume that alpha is irrational. Now, again, here, there's a beautiful theorem by Rudnick and Sarnak from 1998. And they prove that the 2-point correlation function of this sequence is the same as for a Poisson point process in the limit, provided alpha is typical, generic, with respect to Lebesgue measure. So again, this statement only holds for a set of full Lebesgue measure. However, we really, really believe here that this should hold, for example, for alpha equals square root 2. So should be true for alpha is square root 2. No one knows how to prove this. This is really a mystery. We don't even know if the gap distribution is converging for almost every alpha. So that's also an open problem. And you really need to appreciate that, you know, it's such a simple sequence. So, you know, just take the values n squared times square root 2, and you take the fractional parts. You know, everyone can write this down. Even I can do a little numerical experiment using Mathematica or Python or whatever. And you can plot this distribution. So this is the gap distribution for exactly this example here. And you just work out the gaps, then you plot a histogram, and you see it follows the exponential distribution. So we really, really think that this should be the answer, but we can't prove it. We can't even prove it for almost every alpha, that there is an exponential distribution in the limit. And some very, very good number theorists have worked on this. So, you know, that's really also a challenge to the probabilists and the statisticians in the audience. The key problem here is that the sequence is no longer exponentially increasing, but very slowly increasing. So you get really lots of correlations between it, which nevertheless seem to disappear in this particular limit. Here's a theorem that I proved where we can say something about a specific alpha. So this is this sequence where you take n minus alpha, you square it, and then you divide by capital N, okay? So don't ask me why I started studying this sequence. There is a motivation from mathematical physics. There's a very nice paper by Stephen Zelditch who looked at the sequence first. And the nice thing here is that actually this is true. This theorem is true, for instance, for alpha is square root 2. And I'm always very proud about this because in almost every result, like for almost every alpha, still has sort of a probabilistic flavor. It's still, in a sense, if you like, not really a deterministic sequence. But here it is completely fixed. Alpha square root 2, there's no randomness in the sequence whatsoever. The price we have to pay, unfortunately, is that we can't prove this for the 2-point function on the nose, but we have to apply some averaging here. So we need to average the truncation parameter n over a small range. And otherwise, we can't prove it. We really believe that this should be true, also without this averaging. And again, here's a numerical experiment for the gap distribution, where again we can't prove anything. Right, now I've talked about the Rudnick-Sarnak result. So Rudnick and Sarnak assumed that you looked at a polynomial of degree greater or equal to 2. So but what about d equal to 2? So in this case, you see, we just look at n alpha mod 1. And so we just look at the fractional parts of n alpha, where n goes from 1 to capital N. And there, of course, you can also do the little numerical experiment for a fixed alpha. I've chosen alpha square root 2 here. And what you realize when you do this is you only see 3 values that appear in your histogram. So before we saw an exponential gap distribution for higher order polynomials. Now in this linear case, we only see 3 values. And that's kind of striking when you look at it at the first time. And that is a phenomenon that's been understood since the 1950s. Steinhaus was the first to see this. He couldn't quite prove it, but almost immediately, so Steinhaus was an Hungarian mathematician, and almost immediately and independently, 3 Hungarian mathematicians then proved this fact. So what is the statement here? You take n alpha, so you take alpha, 2 alpha, 3 alpha, 4 alpha, and then you stop at some point and you ask what are the gaps between the sequence if you take fractional parts. And the statement is that there can only be 3 values that can appear. These values will change as you increase n or as you vary alpha, of course. But it'll only be at most 3. It can be 2, it can be 3. If it's 3, then the third value is the sum of the previous 2. So that's the 3-gap theorem. And as I said, it's been proved over 50 years ago. And the proofs are simple, but they're not sort of completely trivial or elementary. You need to think to do this. What I wanted to just explain to you is recently we found a very nice proof, if you like, in one picture and one image proof of this theorem that uses the space of lattices. And the space of lattices is something I've been working on for a while. And in particular, the beauty of this approach is allows you to actually generalize these kind of statements to higher dimensions. So I just wanted to give you that little proof of the 3-gap theorem now in this situation, and then tell you a little bit about how that generalizes to higher dimensions. And then we'll again return to the randomness, because obviously this sequence is not random at all. The gap distribution is very non-generic. Okay, so we are interested in the gaps of this sequence, K alpha mod 1. And so now, how do you work out the gap here? Well, what is the gap? The gap is the distance to the, so if this is our unit interval here, and this is psi k, then the gap is the distance to the next element to the right. Yeah, and so that would be psi l. And so in this formula here, that's all I've written up here. It's the minimum of all the other L's, so that L minus K alpha is the smallest. And then I also take this n here. That's really important because that's taking the fractional part. That's the mod 1, right? So n goes here over all integers. And L, of course, goes over all, goes from 1 to capital N. Now, I'm assuming here that it's strictly greater than 0, because what I'd like is that, of course, it's not L equal to K. I don't like. I really want the next one to the right. So that's why it's strictly greater than 2. Now I make a simple variable substitution where I just shift L by K, and I call this M. So nothing's happened here, really. I've just shifted it. And of course, I need to remember that L appeared here, L appeared here, but this is a lattice. So shifting things by an integer vector doesn't change my lattice. That's good. But here something new happened. So I've now shifted the interval by K, and then my M, which is now really the difference vector L minus K, is in this interval. And now here's the big trick. The big trick now is to realize that you can think of this minimum actually as the smallest height of a lattice point, and now a lattice that's been sheared. Okay, so how do you see this? Well, just plug in what is x here. xy is now a lattice point in this lattice. And so let's just work this out, and then you see exactly what I mean here. If you work this out, well, what do you get? You get m, and here you get n alpha plus m. And that's, no, that's wrong. You get m plus, yeah, m alpha plus n, right? So this is from the second column. And so you see here, this is exactly the second component of such a lattice vector. So in other words, we can represent the gap in the sequence as the height, the height of a lattice point that falls into, whose first component is in this interval here, and whose second component is minimal. So that's exactly the picture you see there. And this interval here is simply this interval there. Yeah, and so now, now what we say is, okay, let's just forget about the fact that we started off, that we chose a particular matrix A1 here. Just let's replace A1 by a general matrix M. We notice here that A1 has determinant 1. And so let's replace A1 now with a general determinant 1 matrix. So that's what's happening here. So I'm now defining a function that gives me, if I start with a lattice, a general lattice Z squared M, and it selects the smallest height of all lattice points whose first component falls into a certain interval. And that interval has width 1, and it's parametrized by t. Okay, and if you then remember the previous slide, what you can see is that we can now represent the gap of psi k to its nearest element to the right as this new function that's evaluated with this particular matrix, and where t is this particular choice kn. You're happy with that? It's really just, you just need to put it in. There's no higher mathematics that's happened here. It's really very, very simple. But the conceptual point is to simply say, I now have a I now am allowed here to just take any matrix M, and then for a special choice of M, I get what I want, okay? And why is this an advantage? Well, the advantage is that what we now can think of forgetting about capital N, we can forget about K, and we just need to analyze this function MT. And the important thing is that this function is invariant under this group SL2Z. So we can really think of this function that it's a function that lives on the space of 2 by 2 matrices with determinant 1, and it's invariant under this discrete group gamma. That's a beautiful homogeneous space. It's the modular space, and we know a lot of things about this space. But just to give you now the one picture proof of the 3 gap theorem that I've promised you, is now we can actually state it in terms of this function fmt. This in fact works for any m, not just the m that corresponds to our original problem. It works for so that's really what sort of made us very happy. And so here is the statement. So the first one is what I've just said. It's an invariant function under gamma. And why is that? Well, if you replace m by gamma m with gamma in SL2Z, so SL2Z is 2 by 2 matrices with integer entry and determinant 1, then you see nothing changes, right? And why is that? Because the z squared is actually invariant under those matrices, SL2Z, right? That's the beauty of it. That's the key observation. So first of all, it's well defined as a function on this space. It's invariant. The minimum always exists. One can prove this. And then secondly, if you look at the values that this function takes as we now shift t. So remember, this was the main observation here, that the kth gap is given by our function where t is evaluated at k over n. So if we now want to understand how many different values for skn we have, if I understand how many values my function can take as a vary t, that also gives me an upper bound, okay? So this is exactly proposition 2. First of all, this function is piecewise constant as a function of t, and it can take at most 3 values. And that implies the 3 gap theorem. But it does even, it gives you even more information, right? It works for any m, it works for t as a continuous variable. And let me just see how we prove proposition 2. So remember, what was the function fmt? It gave you the height of the smallest height of all the lattice points that fall into this green strip. And now we move this green strip and we just want to understand which lattice points can actually arise as the ones with the smallest height, okay? So let's just look at all lattice points in the full strip, -1, 1, because that's where our green strip is moving around. And let's start with the smallest height lattice point in that big strip from -1 to 1. Let's say it's R. It could be on the right half, it could be on the left half, it doesn't matter. Let's assume it's on the right half. Then let's take the next one, the lattice point that has the second highest height. So then you can actually show it has to be on the left half as the first one is on the right half. And then it's just a little small combinatorial argument to show that if you miss R or S, the only other point that can have sort of the smallest height for this green strip as you shift it around can be R plus S, the sum of the two. Okay, so I hope you see this. So we have this strip from -1 to 1. We look at all the lattice points that are in this strip, and then we have this green strip which we move around in there. And you're asking, well, as I move this green strip, how many lattice points can there be that as I move the green strip, that in each green strip, that lattice point gives me the smallest height. So there can only be 3 lattice points that can arise in this way. I mean, I think you almost see it now. it's just to make sure that everything's correct. And you know, do have a look at our little paper here in the American Math Monthly, or if you want to run an undergraduate project, I think this is quite nice because it gives students an entry to this beautiful theory of the space of lattices. Right, so I'm not going to talk about this very long because also tell me when I should stop first of all.
So it's for an hour, say we started
Okay.
at 2:31 and maybe another 20 minutes.
That's perfect, yeah.
Yeah.
So I don't want to talk about this too long. This is one of the higher dimensional generalization. It's a paper that I've just finished with my friend and colleague Alan Haynes in Texas. And you can ask yourself, well, how about the same question in higher dimensions? So take a unit box, identify opposite sides. So then the kind of topology you get is that of a torus, right? So you glue things together. And you take now as well, you take a vector alpha, and then you iterate that. So you just take iterates of this vector. So you would be here, but then you glue things together. So you come back in here and you go on. And that's sort of a very natural higher dimensional generalization of the one-dimensional problem I just showed you. And now, you know, one of the things you're interested in statistics is the distribution of points in higher dimensions and what are the, for instance, distribution of distances and so on. So that's also a very natural statistical test of a higher dimensional sequence. And what we found here is if we ask how many distinct values you can get as the distance to the nearest neighbor. So we just say, okay, now we have these here and you look at the distance to the nearest neighbor, they can be at most 5. And we use exactly this approach that I just showed you on the previous slides because this really generalizes to higher dimensions. Here's just an explanation. So here you see what I've just tried to draw by hand. You start with the point 1. So that is, so the vector alpha that you see here is this vector. That's alpha. And then you see this, and then we iterate, and then this is the second point we get. So this would be alpha, this would be 2 alpha, and so on. 3 alpha would be here. 4 alpha, 5 alpha, 5 alpha, and then you wrap around again, and so on. And what you see in this graph, let me just erase what I've just shown and so you see better what I'm talking about, is now the vectors that show you the nearest neighbor. So for instance, the nearest neighbor of this point, number 4, is 9 alpha, point number 9, right? That is the nearest neighbor. However, the nearest neighbor of point 9 is point 1, and the nearest neighbor of point 1 is point 9. And we've listed them all here, and you see that there are at most 5 values that can arise. So for instance, the numbers here, the blue labels, they indicate when you have the same length. So 4 to 9 has the same length as 1 going to, or 6 going to 1, and so on. So this is just a numerical example, and n is very small. The question now is if n is 1,000,000, do you still only see 5 distinct distances to neighbors? This is a 3-dimensional situation, and there we see, in this particular example, we see 12 distinct neighbors. And here's the theorem. So the number of distinct distances to nearest neighbors that you can see in these higher dimensional point sets is bounded above by 3 in 1 dimension. That was the 3-gap theorem. 5 in 2 dimensions. And in higher dimensions, our bound is actually not very good. It's related to the so-called kissing number. It's a number that tells you how closely you can pack spheres. all I wanted to say here, I don't want to talk more about it because I want to come back to sort of the truly random sequences, it's a kind of interesting phenomena. And in particular, it seems such a simple thing and very few people have looked at this. So if you're interested in this, have a look at our paper with Alan, which is on the archive. And I'm not, all I want to say is that the real key step here is, again, to translate this problem into a problem of the space of lattices. Okay, great. So what have we looked at so far? So we've looked at the very non-generic situation when we look at linear sequences, mod 1, and there we don't have convergence. As you've seen, we only get 3 values, but they keep changing as you increase capital N. So actually, you don't have convergence of those gap distributions to a limit. You have convergence along subsequences, but no unique limit. On the other hand, when we look at higher order polynomials, we can't prove anything. So in the linear case, there's a really beautiful thing that you can do is you can just randomize alpha. So let's treat alpha as a random variable. I promise we look at deterministic sequences, but if things are so ungeneric, let's just randomize alpha. So now we think of alpha being uniformly distributed in 0, 1. And then you can prove something. So here now, this is the gap distribution for a given alpha. So I've just highlighted it here. And then we integrate it or average it over all alpha. And nu here, in fact, can be an absolutely continuous measure with respect to the Lebesgue measure. It doesn't just have to be the constant measure. So we can throw alpha random with respect to sufficiently nice distribution. And then you can prove that that then will converge to a limit. And I've showed you here how the limit looks like. It's a function you can calculate analytically, very beautiful function. And people use continued fractions, dynamical systems to establish that, that fact. And my contribution here to this was to actually show how you can use dynamics on the space of lattices to prove such a statement. And again, that will generalize to higher dimensions. So you see, there's a very beautiful distribution here. And let me just briefly explain to you how this can be proved for the using the space of lattices. Okay, so what is the space of lattices? So the space of lattices is, you start with your favorite lattice, ZD. We all know what this is. It's just, a lattice with a cubic fundamental cell. And now you can get any other lattice that has the same co-volume, which means the volume of your fundamental cell. We want that to be 1. And by just applying a matrix SLDR, and I'm thinking of my lattice points as row vectors. So I'm multiplying here from the right, and that gives me a new sheared lattice. And in fact, any lattice can be obtained in this way. And now, as you've noticed before, ZD is invariant under SLDZ. So the space of lattices is really the coset SLDR modulo SLDZ. So SLDZ is the stabilizer. And it turns out this is a beautiful space, has great topology, and you can endow it with a measure that's finite, a finite measure. So it is actually a probability space, and you can therefore make sense of the notion of a random lattice. And that probability measure comes from Haar measure on the Lie group SL2R. So you take your Haar measure on SL2R, you restrict it to a fundamental domain of this quotient space, and then you normalize it to be a probability measure. So this were things that were already known to Minkowski and Siegel over 100 years ago. But the beautiful thing is now we're in the realm of actually doing ergodic theory. And so if you just recall what the function we were interested in here was, it was this function fmt, which we knew was a function SL2R modulo SL2Z. And we were evaluating it at this particular matrix. Now, when we now look at an average over alpha, the question is, well, what happens if I average over alpha in the space of random lattices, right? So really, I'm interested in here in such an object where I take my lattice C2, I shear it by alpha, and then there is this parameter capital N, which you remember was simply the truncation parameter. We look at the first n values of our n alpha mod 1. And then what this theorem here says is that indeed, if you average over alpha in the space of lattices, so you need to think about this lattice that's now randomly sheared and stretched by n, it converges to a limit. And this limit is given by Haar measure. So in other words, what this says, and you can think of the lattice here really as a random point set. This random point set is sheared and stretched, and it converges to a new random point set that's given by a random lattice with respect to Haar measure. That's really what this theorem says. So you couldn't even make sense of this in sort of distribution of random point sets by saying this converges to z squared m, where m is distributed according to the Haar probability measure. And this theorem can be proved, for instance, by the mixing property of the flow generated by the right action of phi t. It works in any dimension, and in fact, these kind of statements work for much more general homogeneous spaces, G mod gamma. And of course, I can't give a talk here about this without mentioning the people who were the absolute pioneers in generalizing these kind of results to general Lie groups, in particular Raghunathan, who made very influential conjectures, which were then proved by Marina Ratner and are now known as Ratner's theorems, which give you a full classification of those measures that are invariant under certain subgroups acting on Lie groups. And this is really what allowed us to generalize what I've just showed you in this very simple case of 2x2 matrices to arbitrary Lie groups with some beautiful applications. And furthermore, Dani and Margulis, again, you know, pioneers in this area who contributed to the development. In particular, Dani's Margulis work set the foundations of Ratner's breakthrough. And they're still active. And I met both Dani and Raghunathan last year when I was in Bangalore. They both attended that workshop at the Tata campus. And also I wanted to say, and that was to me a huge surprise when I read those papers, Olaf Kallenberg is one of my heroes in probability theory. He's written some really beautiful textbooks, and he rediscovered the space of random lattices. As you see here, an affirmative answer is further given to the question whether there exists a lattice type point process in the plane which is stationary and arbitrary under area preserving transformations. That's exactly what I've just constructed for you on the previous slide. And actually, John Kingman pointed that out to him in a letter which Kallenberg reprinted. And just here, I'm quoting from the letter, and you see everything's here. SLNZ, SLNR modulo SLNZ, and so on. And he explains exactly how this fits into this well-known theory. So this is known in integral geometry, of course, as well. But I was very impressed how knowledgeable Kingman was. And of course, also Kallenberg's sort of rediscovery of this fact. Now, so I hope I've given you a little illustration on that. Now, just very few
Jens,
more
one
comments.
Question.
Yeah, question?
Yeah, in this case, the convergence of the lattice type point process, is it essentially the convergence of the matrices itself will give you? I mean,
yeah,
everything is given by the 2x2 matrix. So it's essentially.
Exactly. So yeah, you have a map. There is a continuous map between the two. The point processes and the matrix, and of course the rate of convergence depends on which test functions you put in, so they need to be sufficiently regular.
Okay.
Okay, so here is sort of coming back to the small powers. n to the beta. And if you put that on your computer, so this picture is n to the 1/3, and then we take fractional parts and we look at the gaps, it's exponential. No one can prove this. Okay, it's a mystery. It's such a simple problem. No one's able to prove this. However, if you look at the fractional parts at n to the 1/2, you don't see an exponential distribution. In fact, you only see a non-generic distribution, for all I know, when the power beta is 1/2. For all other powers beta between 0 and 1, you see exponential distributions. And here again, ergodic theory, in fact, Ratner's theorem is used to prove that the limit distribution, limiting gap distribution exists, and we are able to calculate an explicit formula. When I say we, it's not we really, it's Elkes and McMullen who really in a beautiful paper were able to prove this. My contribution here was to look at the 2-point correlation function, and it's really surprising. The 2-point correlation function converges to that of a Poisson point process, even though the gap distribution is completely non-generic. So that's, of course, not a contradiction, because you will have 2-point statistics who are compatible with a Poisson point process, even though the full distribution isn't, right? So second-order statistics don't determine the distribution. But it's nevertheless surprising here that this happens in this particular example. And okay, you can look at many other statistics, for instance, directions of points. But given the time, I don't want to tell you too much about it, except to say that if you look at a lattice and you record the directions of all the lattice points in a big ball, and you look at the gap distribution, it will be the same as for square root n mod 1. And again, that's maybe a mystery, but if you read our papers, the mystery will clarify. And the reason behind it really is that although these two sequences are completely unrelated at first sight, they both live on the same space of lattices, and you have equidistribution to the same limiting measure. So that's really what is behind that. Okay, so just as an illustration, but look, let me skip this. I'm just going to show you those pictures here because they're kind of beautiful. You see the square root and yeah, no. I want to finish with something else. If you want me to explain those pictures that I just showed you, which somehow explain why the statistics are the same for the directions of lattice points and square root n mod 1. I'm happy to do that, but I don't want to go over time. I know you're all busy. I just wanted to come back to the fractional parts of log n. So not firewood log, which is out here in my garden, but log n mod 1. And so what is really surprising here, we do start seeing an exponential distribution. So what is this? We look at log b. B is the base of the logarithm. So you can look at log n mod 1, of course, with respect to the exponential base. But what we want to do here is we want the base to be transcendental and very close to 1, for instance, in this example. And so when you do then your numerical experiment, it looks as if it's an exponential distribution. And so log n is really one of the sequences you think are far, far away from being a random sequence, even if you take fractional apart because it's growing so slowly. Nevertheless, the gap distribution looks almost exponential. Now we can calculate the difference with the exponential distribution, but we also can prove that it actually converges to the exponential distribution if the base is transcendental and closer and closer to 1. Okay, that's it from me. So I hope I've given you some challenges here on some really simple number-theoretic sequences, which you can write down, where the only randomness is generated, if you like, by taking the fractional parts. And I think it's remarkable that even for a sequence like n squared alpha mod 1, we can't prove that the gap distribution converges to a limit, and can't prove that that limit should be an exponential distribution. So if you want to read more, I really recommend to have a look at this paper if you want to learn more about this. And in the other papers, we've always tried to read write the introduction in such a way that they're informative. So I hope you'll enjoy that, and please do get in touch if you have questions. Of course, I'm happy to take questions now. Thank you.